Okay, well, welcome to this example. Today what we're going to do is look at kind of a simple rack and pinion system. In particular, what we have here is a rack A, which moves to the right with a speed of VA and an acceleration of AA, and a second rack, rack B, which moves to the left with a constant speed of VB. In given numerical values for VA, AA, VB, R, and R, that is the inner and outer radius of the gear respectively, we're asked to determine the velocity of point P on the outer rim of the gear, as well as the acceleration of the same point. Now to help us out here, we're going to use a Cartesian vector set, and so I'll choose to go ahead and define unit vectors along the I and j directions that we've been used to using, and we'll see how we can use those for great effect. Here what I'm going to try to do is I'm going to try to relate the points where I know the most information to start. And in this case, probably the points where I know the most information are going to actually be, in this case, at the point in contact with the upper gear and the point in contact with the lower gear. And I'm going to see if I can use these to help me out. So in this case, what I'm going to choose to say is that because there's a no-slip contact at both the top and bottom intersection of the gear with the rack, then we note the velocity of the gear at the points in contact have to match the velocities of the respective racks. Or maybe more accurately, what I can say here is if we reference this point on the gear to be point A and point B, at least in some extent, or perhaps more accurately the point of the rack in contact of the gear, what we can say here is that the velocity of point A, for example, has to equal the velocity of point B plus the angular velocity of the rigid body cross r of A with respect to B, where of course in this case the rigid body refers to the gear. Now you might say, well, how does that get us to the velocity of point P? Well, what I want to try to do here is extrapolate information on the angular velocity of the system, because of course we're going to need that to recover the velocity of point P. So if I do this, what I'm going to end up with here is, first of all, I'll have the scalar result for VA, which we know is purely in the I direction. And we'll say this has to equal VB, which we know is some scalar in the minus direction. In fact, let's just write this as a positive quantity and keep in mind that we could plug in VB being a negative number. Actually, I take that back. Let's go ahead and add the negative sign to be consistent with the fact that we say VB is moving to the left with the amplitude given as a positive number. So we'll make this minus VB in the I, and I'm going to add to that omega in the K across the position vector of R of A with respect to B, which in this case is going to be quantity big R plus little r in the J direction. So if I go ahead and expand this out here on the right hand side, I'm going to have minus VB in the I, and then K cross J is going to give me minus I, so I'll have minus omega times quantity R plus R in the I as well. At this juncture I can simply pull off everything that's multiplying the I direction. And if I look at terms that are in the I direction, I'll have on the left hand side VA, and on the right hand side I'll have minus VB minus omega times quantity R plus R. Now if I use this, I can go ahead and solve for the angular velocity directly, and if I do that, I'll have that omega is going to equal, in this case we're going to have VA plus VB divided by quantity R plus R with a negative sign out in front. Maybe we'll write it like such. And if we want to make this a vector, we can simply append the k direction because we know the rotation will be about the k-axis. Okay, so now that I have that, of course the question is, can I do something similar for angular acceleration, because I'm going to need that as well. And here I have to be a little bit more careful. We know the no slip condition implies that there's no slip or relative acceleration in the x direction, or the horizontal direction at the points of contact. And so we need to be careful and keep that in mind as we look at relationships involving acceleration. So in this regard, what I'm going to go ahead and say here is that if I call the points immediately below A and B here, or if I call A and B to be on the gear, I'm only going to have continuity with the rack in the x direction. So here's what I'll do. I'll say the acceleration of point A is going to equal the acceleration of point B plus the angular acceleration of the rigid body across R of A with respect to B. And then because this is a planar problem, I'll subtract from that omega squared times the position vector of A with respect to B. Now at this point, what I can say is that the acceleration at point A will be the scalar AA you're given in the I direction, plus an unknown component in the Y, which I'm going to call AAY. And then that's going to equal a component which we're told is 0 in the I, plus an unknown component in the Y direction, which of course will be the J. I'll add to that the unknown alpha and the K, cross the position vector of A with respect to B, which is quantity R plus R in the J direction. I'll subtract from that the scalar value of omega squared. We've just found omega, and then I can multiply that by also the position vector of A with respect to B, which is r plus r in the j direction. If I expand what's on the right hand side here, this is going to give me ABY in the j. K cross j is negative I, so I'll have minus alpha quantity r plus r in the I, minus omega squared times quantity r plus r in the j. At this juncture, I can say, well, how could I get out alpha? Well, we'll note that the alpha term here appears in the I direction, and only the I direction, so if I pull out just the I direction here, I'll get the very tidy result that the acceleration at A, the new scalar value we were given, is equal to minus alpha times quantity r plus r, which of course tells me that the angular acceleration alpha is given by minus AA divided by quantity r plus r, and if I want to make this in vector form, I'll append the k. Okay, great. So now we've found the angular velocity and angular acceleration. We can use this to our advantage to actually find the velocity and acceleration associated with point P. And here's how I'm going to do that. What I'm going to do is I can start with the velocity, and I can say the velocity of point P is going to equal the velocity of a point that we know exactly on the body. I'll choose to, in this case, point A, plus the omega vector we found cross the position vector of P with respect to A. I can go ahead and do some substitution here. I know the velocity of point A is some VA in the I direction. I'm going to add to that an omega in the k direction, where I've already found omega, and I'll cross that with the position vector of P with respect to A. If I go back up here, what I can find is that the acceleration of P the position of P with respect to A is going to be, in this case, and I'll write it here for the first time, P with respect to A, is going to be a distance r in the I minus little r in the j. So if I plug that in, I'll have capital R in the I minus little r in the j. If I go ahead and expand this out, I'll have this is equal to VA in the I direction. K cross I is going to give me a j, so I'll have plus omega times big R in the j. K cross j gives me minus I, so I'll have plus omega times little r in the I. So if I group this together here, look at the velocity of point P is equal to VA plus omega r in the I direction plus omega times big R in the j direction, where omega, of course, is the value that we've already determined up above. Now I can do something similar now with the acceleration itself. And so if we do this, we can get that the acceleration of point P is going to equal the acceleration of a point that I know on the body. In this case, perhaps maybe I'll choose point B, plus alpha cross r of P with respect to B, minus omega squared times the position vector of P with respect to B. Now, how can I work this out? Well, I can go ahead and plug in here. I don't know AB exactly, but I know it's purely in the y direction, so I'll have ABY in the j. I'll add to that a known value alpha in the k, and I'll cross that with r of P with respect to B. If I go back to my drawing yet again, we'll see that r of P with respect to B is equal to big R in the I plus big R in the j. So if I come down here and plug that in, I'll have this be big R in the I plus big R in the j. And I'll subtract from that omega squared that we've already found times quantity big R in the I plus big R in the j. So if we go ahead and expand things out here, I'm going to have this is equal to ABY in the j plus k cross I is going to give me j, so I'll have plus alpha r in the j. K cross j is going to give me minus I, so I'll have minus alpha r in the I, minus an omega squared capital R in the I, minus omega squared capital R in the j. If I group this all together here, I'll have that AP is equal to quantity minus alpha r minus omega squared r all in the I, plus quantity ABY plus alpha r minus omega squared r all in the j. Now those of you that are observant here as I've gone through this process realize we haven't identically found AP yet because I still have ABY in our result. We need to have some way to eliminate this term. And so to help us out with that, I've got to figure out another way to get rid of ABY. You might think to yourself, well, how could we do this? Well, we could go back to the equation that I'm highlighting here and look at the j component, because we know that relates ABY. But what one would quickly realize is that also involves AAY. That doesn't seem like it's going to help us out too much. Is there something else we might be able to do? Well, let's go back to the picture. Is there some point on this body where we actually know the acceleration in the y? That's what we need to help us out. The answer is actually, yes there is. Namely, it's point O. We know that point O has to follow a horizontal path, which means the acceleration of this point in the y direction has to be 0. How does this help us out then? Well, what we can do is try to solve for this unknown ABY. And the way I would probably suggest we do that is simply to write down that the acceleration of point O has to equal the acceleration of point B plus alpha of the rigid body cross r of p with respect to B minus omega squared times r of p with respect to B. Excuse me, not p with respect to B, but rather O with respect to B. Sorry about that. Now we can do some substitution here. We'll have that AO has to be purely in the I direction. AB we've already said is some ABY in the J. I'll add to that alpha in the K, cross R of O with respect to B, which is R in the J, minus omega squared R in the J. I expand the cross products here. I'll have ABY in the J. K cross J is going to give me I, so I'll have minus alpha R in the I, minus omega squared R in the J. This is a pretty nice equation because if we look at this, we realize that if we pull out simply the J component, we have that 0 is equal to ABY minus omega squared times big R, which of course gives me that ABY is simply equal to omega squared R, and we can take that value and substitute it in right back here and get an answer for the second term we were asked for, namely the acceleration of point P. So if I rewrite that down here at the bottom to get our final result, we'll have the acceleration of point P will equal quantity minus alpha R minus omega squared R all in the I direction, plus quantity omega squared R plus alpha R minus omega squared R in the J. And if we look carefully there, we'll note that two terms actually cancel out. And so we'll end up with the net result that the acceleration of point P is equal to minus quantity alpha R minus omega squared R all in the I plus alpha R in the J. And I think that about wraps us up. Best of luck.